As we shall see, sea levels are very closely tied to Earth's climate, and this has changed dramatically through the millions of years of Earth's history, progressively cooling over the last 15 million. The Earth's climate is of course largely driven by the Sun, but many factors can affect it. Changes in Earth's tilt and its orbit around the Sun, changes in the Sun's own activity with 11 and 90-year cycles affecting cloud formation in Earth's atmosphere, large-scale tectonics, movements of the Earth's crust causing uplift or sinking of land and ocean floors and affecting major wind and water currents, ash and gases in the atmosphere from countless volcanic eruptions, and resulting from combinations of all these factors, many huge natural weather cycles lasting from years to centuries. Recently, over the last 2.7 million years, the climate has cycled between climate extremes, glacials or ice ages, and interglacials or warmer periods. These are triggered by regular changes in the Earth's orbit called the Milankovitch cycles. We are currently in an interglacial or warming period. More recently yet, human activity has added to climate change by changes in land use and removal of natural vegetation from immense areas of land, and most importantly, by an increasing level of greenhouse gas emissions like carbon dioxide, methane, and nitrous oxide, primarily from the use of fossil fuels, which has increased rapidly since the mid-20th century. This is causing significant warming and sea level rise. To see how climate affects sea level, we need to go back to the glacials and interglacials. During a glacial, the sea level falls. 2 reasons. With cooling, huge ice sheets form on land and lock away large volumes of water, and liquid water contracts on cooling, so at very cold temperatures, ocean volumes shrink. Both these processes result in less water in the oceans. The sea level falls. In the last glacial 20,000 years ago, the sea level was 120 meters lower than today, and new land was exposed. During an interglacial, the sea level rises. Again, 2 reasons. With warming, the huge land-based ice sheets and glaciers melt, returning large volumes of water to the oceans. This can happen suddenly or slowly. For instance, it has risen 120 meters in the last 20,000 years, at rates varying from less than 1 millimeter up to 45 millimeters per year. And liquid water expands on heating, so as the water is warmed, the oceans grow in volume. Both these processes result in more water in the oceans, and sea level rises. Rising sea levels in our present interglacial have flooded land which was exposed during the last ice age. Today we measure sea level in 2 ways, by satellite radar or by land-based tide gauge. Satellites give us a global average sea level, an average rise of 3.3 millimeters per year over the last 25 years. Tide gauges, on the other hand, measure local or relative sea level. This may be quite different from the global average and is the most useful to local communities. The New Zealand average increase over the last 100 years has been 1.7 millimeters per year. Local sea level can be affected by many things. Land rising or falling due to tectonics, or often rebounding after ice is melted. For instance, at Haumoana in Hawke's Bay, land subsided about 70 centimeters during the 1931 earthquake, and the shoreline has since moved 40 meters inland. While New Zealand overall is rising slowly at 0.33 millimeters per year, much of the lower North Island is sinking at rates between 2 and 8 millimeters per year, and some areas in the Bay of Plenty are rising at up to 10 millimeters per year. These will all reduce or increase local sea levels. Local sea level is also very affected by natural long-term weather cycles, involving changes in wind, air pressure, ocean temperature and rainfall. For instance, in New Zealand, the sea level falls during an El Niño phase and rises during La Niña years. and sea level can be affected by changes in the amount of water held on land. Dams and river capture for irrigation reduce the amount of water returned to the oceans, thus lowering sea level locally, whereas deforestation and loss of wetlands increases water returned to oceans, and local sea level rises. Can we predict how much and how fast sea level will rise? Not accurately. Sea levels depend on a large number of combinations of many factors. What most countries do is work with a range of possible changes. These are largely based on reports issued every 6 years by the United Nations IPCC, a panel of scientists from around the world which reviews scientific work on climate change and human causes. The reports contain updated predictions of global warming and sea level rise, based on different scenarios of greenhouse gas emissions. They also predict likely impacts and possible ways to adapt. The latest assessment suggests a global sea level rise of between 50 centimetres and 1.5 metres over the next 130 years, depending on emission levels. Much more work is being done by the New Zealand Sea Rise Programme to improve predictions for the whole country. How will sea level rise affect coasts? In general, continued sea level rise will cause coastlines to creep inland. Low-lying land may be gradually inundated. Hard rocky shores will see a simple rise in water level. Soft cliffs will continue eroding, but faster. Estuaries and salt marshes may adapt and stay in place, or move inland. How will sea level rise affect sandy beaches in particular? As seen in video 1, sandy beaches are constantly on the move, with sand cycling between the sea and dunes, and shorelines moving to and fro, landward with erosion and seaward with accretion. However, with sea level rise, the new water level moving inland and up the beach forms a continuously eroding front. Given the right conditions of sand supply and space, the whole slope or profile of the beach will migrate inland. The distance moved inland is of course very hard to predict. A combination of many unknowns, such as size and rate of sea level rise, and the character of the new beach territory. A general estimation could be in the order of 1 metre rise in sea level, causing a move inland of 20 to 50 metres. If the beach is trapped between rising sea level and any coastal development, it cannot migrate naturally inland as we have described, and it will become progressively narrower. Coastal squeeze! On beaches with a very large sand supply, from rivers or longshore currents, a beach may continue to accrete slowly and not suffer permanent erosion. On beaches with well-established dune systems, the dunes could initially delay the erosion before the shoreline moves inland.